Okay, I want to take the last 8 minutes of class and talk with you about something that might seem a little exotic, but actually has equally important practical consequences in the real world. And it has to do with the fact that magnetic forces and magnetic fields depend on motion. So if a particle's not moving, it doesn't make a magnetic field. If a particle's not moving, it can't feel a magnetic force. And this is the first force we've encountered that's like this. Gravitational forces just depend on position. Electric forces just depend on position. Having this V in there is really a little odd. And so I want to consider the following situation, which is really a pretty simple situation. Let's consider two protons traveling along together at speed v at some instant. They're going to move, of course, but at this particular instant, they're some distance apart, and they're moving with speed v. And I'm going to call them proton 1 and proton 2 so we can keep things straight. Okay, let's consider 1. I want to find what the force is on 1 due to 2. So first of all, there's an electric force, right? What's the direction of the electric force on 1 due to 2? Up. Okay? So we have this electric force. Now, magnetic forces. It's moving, so it could feel a magnetic force. And this guy's moving, so it could make a magnetic field. So we have to go through two steps to get the magnetic force. The first is we figure out what the magnetic field is here due to this guy, and then we figure out the force. So at the location of proton 1, what's the direction of the magnetic field made by proton 2? This is an equation you had to memorize, remember? Magnetic field of a moving charge. So we've got a V, we've got an R hat. So QV cross R hat over R squared, right? And Q's positive. So the magnetic field is in what direction? Out of the board. V2. And that means the magnetic force on this guy is in what direction? AV cross B down? Down. I will assert that it's smaller because, and you can actually calculate it yourself if you want. So the net force on this guy is actually a little bit less than the electric force, right? Okay, we go through the same thing here. There's an electric force on this guy. We have a magnetic field. This guy makes a magnetic field into the board here. And therefore, the magnetic force on this particle, V, is up. And so we have a net force that's down, right? So basically, these things are repelling each other not quite as much as they would if they weren't moving. And so their paths are going to, what are their paths going to look like, basically? Can you just sort of show with your fingers? Okay, this guy's going to go, and at some point it's going to hit the floor. And this guy's going to go there, and at some point it's going to hit the ceiling. And the force is changing, but we could actually do this computation. It's just classical mechanics. So suppose we do the computation and we say that it's going to take 20 nanoseconds, given the forces, for these particles to hit the floor and the ceiling. Okay? Now suppose, though, that instead of just standing here and watching the particles, we're feeling really energetic. And Josh is feeling energetic, and he decides to run along with the particles. So he's going to run along at speed v next to the particles. So from Josh's viewpoint, here are these particles. What's their velocity? 0 from Josh's viewpoint. So what forces does he calculate on these guys? At this instant, there's an electric force up. And is there a magnetic force? No, because there's no magnetic field, right? Nobody's moving. And there's an electric force down. Is there a magnetic force? So the net force, he actually sees a bigger net force than Jonathan, who's decided to sit still and watch them go by. So Josh sees a bigger force, and he thinks the particles are going to go straight up and straight down, and he applies Physics 1, classical mechanics, and does the calculation. And he predicts that it's only going to take 15 nanoseconds for these particles to hit the ceiling and the floor. And now we have a contradiction. It can't take 20 nanoseconds and 15 nanoseconds, right? I mean, they're going to hit the ceiling and the floor. It can't possibly take both of these times. So we do the experiment, okay? Now, it's a little more complicated because Jonathan's sitting there, but he's sitting here, and the particles are going to hit the ceiling and the floor over here. So actually, Jonathan and Adria synchronize their watches, and then she slowly comes over here, and she gets ready to time when it hits the ceiling and the floor. And it goes by here. Jonathan notes the time on his watch. And they hit the ceiling and the floor, and Adrian notes the time on her watch. And then they get back together, and they find that, yep, it took 20 nanoseconds. Their prediction was exactly right. Well, Josh isn't paying any attention to them. He's running along with the particles, and so when he's opposite Jonathan, he looks at his watch, and he chugs along. And they hit the ceiling and the floor, and he's right there, and he looks at his watch, and he says, yeah, it took 15 nanoseconds. Well, the laws of physics seem to work, but they work in a very odd way. And in fact, when Josh ran by, Jonathan looked at Josh's watch and it said 0. And when we got to here where the particles hit the ceiling and the floor, Adria looked at Josh's watch and she said, my watch says 20 nanoseconds and his watch says 15 nanoseconds. His watch is slow. His watch must be slow. And this is actually, it was this puzzle that actually bothered Einstein. And it was this apparent paradox that led him to think real hard about what was going on in situations like this. And he came to the conclusion that sounds a little odd, but has many practical consequences, that in different reference frames, so in the fixed non-moving reference frame of Jonathan and Adria, and in the moving reference frame of Josh, time ran at different rates. Time runs differently in different reference frames. And this was the beginning. His famous 1905 paper on the theory of relativity is actually called On the Electrodynamics of Moving Bodies for this reason. And it has practical applications and implications for GPSs and cosmic rays and all sorts of things.